Hey everyone, welcome back to the channel where we break down complex tech topics into simple, easy to digest bites. If you're new here, don't forget to hit that subscribe button and turn on the bell icon so you never miss out on these tech nuggets. Now, today's video is something super important, especially for those of you diving into cybersecurity or preparing for the CRISC certification. We're jumping into Domain 4, Asymmetric Algorithms and Hashing in Cryptographic Systems. But hey, don't let the big words scare you off. By the end of this video, you'll not only understand what these terms mean, but also why they are crucial in the world of secure communication and data integrity. So, what's on the plate today? Here's a quick sneak peek at what we'll cover. 1. A quick introduction to set the stage. 2. What exactly are asymmetric algorithms and how do they work? 3. We'll break down the famous Diffie-Hellman model. Yep, the handshake that started it all. 4. The advantages of using asymmetric algorithms. 5. But hey, nothing's perfect. We'll also discuss their limitations. 6. Then, we'll dive into message integrity and hashing, making sure data stays untouched. 7. An overview of popular hashing algorithms. 8. And finally, how hashing helps in ensuring data integrity. So buckle up, because by the end of the session, you'll feel a lot more confident about these essential cybersecurity concepts. Ready? Let's dive right in. Alright, let's kick things off with a quick introduction to set the foundation. So, what's the big deal about asymmetric algorithms and hashing? Thinking phase, why are these terms always floating around in cybersecurity conversations? Here's the simple truth. In today's digital world, keeping our data safe is non-negotiable. Whether it's sending emails, online banking, or even just logging into your favorite social media app, we need systems that protect our information from prying eyes and tampering. That's where asymmetric algorithms and hashing come into play. We're going to focus on 3 key areas today. 1. Purpose. Why do we even use these techniques? Spoiler alert. It's all about secure communication and data integrity. 2. Mechanism. How do they actually work? I'll explain it in a way that even if you're new to this, you'll get the gist without pulling your hair out. 3. Significance. Why should you care? Well, these are the backbone of encryption, authentication, and data protection. Without them, the internet as we know it wouldn't be safe. So now that we know what we're dealing with, let's dive into the how, starting with asymmetric algorithms. Now, let's jump into the world of asymmetric algorithms, the superheroes of modern cryptography. So here's the deal. Asymmetric key crypto systems were developed to fix the issues found in the older symmetric key systems. In symmetric encryption, both parties need to share the same key to encrypt and decrypt data. But here's the problem. How do you share that key securely in the first place? That's where asymmetric algorithms come in. Let me break it down into bite-sized points. 1. Evolution. Asymmetric crypto systems were created to overcome the limitations of symmetric systems, especially the key distribution problem. Instead of sharing one secret key, asymmetric systems used to separate keys. Smart, right? 2. First public example. The first time this concept hit the public stage was back in 1976, thanks to Whitfield Diffie and Martin Hellman. They introduced the Diffie-Hellman model, which allowed two parties to create a shared secret over an insecure channel without ever exchanging the actual key. This was a total game changer. 3. Key generation. So, how does it work? In asymmetric cryptography, we generate two mathematically related keys. A public key, which anyone can know, and a private key, which stays secret with you. These two keys are like a lock and key pair, related, but one cannot be easily figured out from the other. 4. Operation. Here's the magic. The public key is used to encrypt the message. The private key is used to decrypt it. So, even if someone intercepts the encrypted message without the private key, it's just gibberish. And that's the beauty of asymmetric algorithms. They solve the key sharing problem and ensure secure communication even over unsafe networks like the internet. Next up, we'll dive deeper into the Diffie-Hellman model, the handshake that started it all. Alright, now let's talk about the Diffie-Hellman model, the legendary handshake that laid the groundwork for secure communication over the internet. 1. Keys relationship. In the Diffie-Hellman model, we're dealing with two keys that are mathematically related. But, and here's the cool part, even though these keys are connected through complex math, it's computationally infeasible to figure out one key if you only know the other. This means, even if someone gets their hands on the public key, they can't reverse engineer it to get the private key. 2. Public versus private key. Let's break this down. The public key, this is like your email address. You share it with anyone who wants to send you a message. It's used for encryption. The private key, this is like the password to your email. You never share this with anyone. It's used for decryption. So, with Diffie-Hellman, two parties can securely generate a shared secret without ever sending that secret over the network. Pretty mind-blowing, right? This model paved the way for modern cryptography. Up next, we're going to explore the advantages of asymmetric algorithms, why they're so awesome and widely used. Stick with me. Alright, now that we've got a grip on how asymmetric algorithms work, let's talk about why they're such a game changer. Here are the top advantages of asymmetric algorithms that make them the go-to choice in modern cryptography. 1. Secure channel, no prior contact needed. Imagine wanting to send a private message to someone you've never met before. No exchanging secret keys ahead of time. No awkward meetings in dark alleys. With asymmetric algorithms, you can instantly establish a secure communication channel even with zero prior contact. This is the magic that makes things like online banking and e-commerce possible. 2. Scalability solves the symmetric key problem. Here's the thing. In symmetric key cryptography, as the number of users grows, the number of keys needed explodes. It gets messy and unmanageable real fast. But with asymmetric cryptography, each user just needs one pair of keys, a public and a private key. This makes it scalable and efficient, even for networks with millions of users. 3. Author verification. Know who sent it. Now, here one of the coolest things about asymmetric algorithms, they can help you verify who really sent a message. Let me explain this in simple words. The sender uses their private key to encrypt the message. Yep, their private key. The receiver then decrypts the message using the sender's public key. If the message decrypts properly, it proves that the message was definitely sent by the real owner of that private key. This process is how we confirm the author of the message. This is called digital signatures. They make sure that the message is secure and genuine. Pretty awesome, right? But like everything, there are some downsides too. Let's talk about the limitations of asymmetric algorithms next, because knowing the good and the bad is important. Okay, as much as I love asymmetric algorithms, let's be honest, they're not perfect. Even these super secure systems have a few drawbacks. Here's what you need to know. 1. Their slow computational intensity. Asymmetric algorithms are like bodybuilders, strong but slow. Compared to symmetric algorithms, which are fast, asymmetric ones need more power and take longer to encrypt and decrypt data. So, they're not great for encrypting large amounts of data. Do best for small messages and key exchange. Because they're slow, we mainly use asymmetric algorithms for small tasks like encrypting small messages or sharing symmetric keys securely. Here's how it works. Asymmetric algorithms handle the key exchange like a secure handshake, and then symmetric algorithms, which are faster, take over to encrypt the large data. This way, we get the best of both worlds, secure key sharing and fast data encryption. So, while asymmetric algorithms are super important for security, we also need to know where they fall short. Next, we're going to talk about message integrity and hashing. How we make sure no one messes with your data while it's being sent. Stay tuned. This is going to be interesting. Alright. Now let's dive into message integrity and hashing. This is all about keeping your data safe from being changed or tampered with. Because here's the thing, even if you encrypt your message, how do you know it wasn't messed up along the way? Maybe a hacker tried to change something, or maybe the network glitched. This is where hashing comes in, like a bodyguard for your data. 1. Error detection, keeping your message clean. Hashing creates a unique fingerprint called a hash for your message. When you send the message, you also send the hash. The receiver checks the hash after getting the message. If the hash matches, the message is safe. If it doesn't match, something changed, either a mistake or tampering. This helps spot any errors or hacks right away. 2. Fixed length result, same size every time. Here's something cool. No matter if you hash a tiny tweet or an entire book, the hash is always the same size. This makes hashing super efficient and reliable for checking data integrity. So, hashing helps make sure that what you send is exactly what gets received. No surprises, no changes. But wait, what kinds of hashing algorithms are there? Stick around, because we are about to explore the types of hashing algorithms that keep your data safe. Now that we know what hashing does, let's talk about the algorithms that make it happen. So, what is a hashing algorithm? 1. Definition: the data transformer. Think of a hashing algorithm like a machine that takes any data, a message, file, video, and turns it into a fixed size code, the hash. No matter how big or small your data is, the hash is always the same length. It's like giving everything a unique barcode. 2. Example: different algorithms, different strengths. Let's look at a couple of examples. SHA-1 creates a 160-bit hash. It was used a lot before, but is now considered less secure. SHA-512, this one is much stronger. It creates a 512-bit hash, making it way harder to crack. The bigger the hash, the harder it is for anyone to break it or create a fake. These hashing algorithms are like the guardians of data integrity, making sure that if anything changes, even a tiny bit, the hash changes completely. Next, we'll talk about how hashing keeps your data safe in real-life situations. Alright, now let's see how hashing ensures data integrity, making sure your message stays the same from start to finish. 1. Accidental changes, oops-proofing your data. Sometimes, data gets messed up on its way, maybe because of network glitches or random errors. But here's the trick. You hash the message before sending. The receiver hashes it again after receiving. If the hashes match, the message is safe. If not, something went wrong. It's that simple. 2. Intentional changes, fighting off hackers. But what if someone tries to tamper with your message on purpose? That's where digital signatures come in. The sender creates a hash of the message and encrypts that hash using their private key. This becomes the digital signature. The receiver decrypts the signature using the sender's public key and compares the hash with the received message. If everything matches, the message is authentic and untouched. If not, something's fishy. So, hashing protects against accidents, and digital signatures protect against hackers. Together, they keep your data safe. And that's it. We've covered asymmetric algorithms, hashing, and digital signatures, all the super tools that make secure communication possible today. If you found this video helpful, hit that like button, subscribe for more easy tech tips, and drop a comment to let me know what you want to learn next. Until next time, stay safe, stay secure.